again. Welcome to the third lecture of the sixth week. We are in logic coverage criteria. Last two classes I told you about how logic coverage applies to source code. This is a recap slide. We've seen so many logic coverage criteria and using examples of two kinds of programs, thermostat and detecting the type of a triangle. Using those examples, we saw how to practically apply predicate coverage, clause coverage and correlated active clause coverage. These three are considered to be the most useful amongst the various logic coverage criteria. You would have hopefully realized through the examples that we had to do a good amount of work for even a fairly reasonably sized program like triangle type, which had a good number of predicates, to be able to reach the inner predicates and solve for the internal variables, rewrite the predicates purely in terms of inputs. Then they looked very big. And then the tables, getting the tables for active clause coverage criteria was a bit of an effort. So imagine a few thousand lines of code, which is what a standard program is all about, and applying logic coverage criteria to that. It's going to be pretty non-trivial. So there has always been a bit of a debate, when predicates come from these kind of statements and predicates have less than 4 clauses, and if a predicate has more than one clause, then we said in the last class in this slide that active clause coverage criteria is very useful, but we saw through examples that it's usually a little difficult task, right? It needs a lot of human intervention and explicit knowledge about the code to be able to apply active clause coverage criteria and derive the test requirements for these criteria. So there's been a lot of debates in the programming community. In fact, there has been a fairly large school of thought which says that why do we consider active clause coverage criteria? Because predicate has more than one clause, right? At least in those two examples, we saw that predicate had several clauses, sometimes up to 4 clauses. And then solving for the variables in that clause, substituting back to them, taking each clause in turn to be a major clause, filling up the truth table for correlated active clause coverage took a bit of time. So there has been this school of thought that why not rewrite the program to eliminate these many clauses in the predicate, rewrite it to make sure that each predicate has one clause. I'll show you some examples of what it means to rewrite a program. So a lot of people have been thinking, and in fact at some point in time there was a conjecture going around that if you take a program which has a predicate with, let's say, 2, 3 or 4 clauses, then using the semantics of operators like and or, which connect the clauses, you will be able to rewrite the program by breaking the if statements into smaller statements. And it was believed that the resulting program, if I apply predicate coverage, it will be the same as applying active clause coverage in the given program. Very soon it was proved that this is not correct. I'll show you examples that illustrate that predicate coverage in the transformed program is not the same as the desired active clause coverage. It could be correlated, it could be general. Either cases, it may not be the same. We'll see it through examples. Another reason why people believed that predicate transformation is necessary is, remember, I told you how to do source code, classical testing for source code, right, in the third week or something like that. So there we saw this notion of cyclomatic complexity, which determined the number of independent paths in the program. One of the basic conditions in the cyclomatic complexity is when I consider the control flow graph of the program, all the predicates in that should be what are called simple predicates, which means now in terms of logic coverage criteria that we have seen, they should have exactly one clause. So it was recommended that you rewrite the program to be able to do that. Right, so there are lots of schools of thoughts which keep recommending that if there is a predicate which has 3 or 4 clauses, make it simpler, rewrite it. What I want to do in today's lecture is, using examples, show you that it may not always be a good idea to rewrite the program to break down the several clauses in the predicate. It usually doesn't work all the time. We'll see 2 examples. Try to rewrite the predicate which come in these examples and see what are the issues that we will get. Right, so what is the notion of predicate transformation? The process of predicate transformation deals with rewriting the predicates in the program so that they have, in the resulting transformed program, each predicate has only one clause. This obviously involves changing the control structure of the program. Like, for example, if I have if A and B, which has 2 clauses A and B, I break it up, I have to put nested if statements. First test for if A. If A is true, then you test for if B. If B is true, then it means both A and B are true. Then you write the then part of the original predicate here. So it obviously means adding more control structure to the program. A lot of nested if statements, lot of else statements, right? The resulting program becomes very difficult to read. It has too many if statements, too many nested else statements, and you don't know what is happening where, what is going where. And usually because of this, people don't like predicate transformation. Also, programs, large programs, are written and supposed to be maintained for several years, right? So for maintainability, which means a third programmer or a developer or a maintenance engineer who is going to be able to look at your program and analyze it, will find it very cumbersome if you had written these complicated nested if then else to be able to just simplify for the sake of avoiding predicates with multiple clauses. It doesn't work. I'll show you why using two examples. Here is a small program fragment. It's only a program fragment, not the entire program, meant to illustrate issues with predicate transformation. So this program fragment has two clauses, A and B. There is a predicate here in the if statement which says if A and B, then you do statement or set of statements S1. S1 could be any statement, single statement, a block of statements, could have if again inside that, could have other decision statements like while, could have function calls. We don't care about it. We just abstract it out, call it S1. So this clause says if A and B do S1, otherwise you do S2. This is just a small fragment. Now the predicate under consideration is this one, A and B. As you can see, it has two clauses. So I want to, let's say, apply correlated active clause coverage criteria to this predicate. I want to apply CACC criteria for this predicate. Now what you have to do, you have to do the same old exercise. A be the major clause, work out PA, that is when A determines B, and then consider B to be the major clause, work out PB, which says when B determines B. Put them together to obtain correlated active clause coverage criteria where A becomes true false once, B becomes true false once. We worked out the same example, P is equal to A and B, when we did this in the slides, and inferring from those slides that we did for CACC for A and B, here is the TR. I'm not redoing it, you can refer back to those slides. The final test requirement for CACC for A and B will be this. How do you read this? The first pair says make A and B true. Second pair says make A true, B false. Third pair says make A false, B true. Between these three, correlated active clause coverage is completely satisfied for the predicate P, which is A and B in our case. Now, the goal is, we are looking at program transformation. This predicate has these two clauses. For some reason, I don't like it. I don't want to do the CACC criteria. I want to break these two clauses and rewrite this program into a program that has predicates that contain exactly one clause. So here is an attempt at rewriting this program in this slide. If A and B do S1, else do S2, is rewritten like this. How do we understand what this is? So if you read this program, it says if A, then you go here, then you test for if B. So let's say both these ifs pass, then what does it mean? It means A is true and B is true. Or going back by the semantics of the given program, A and B are true, then what do? I do S1. It's the same thing that I do here. If A is true and then B is true, I do S1. Else, this else is for this if, which means A is true and B is false. So A and B is false, then I do S2. What does this one say? This one is the else for the first if here. It says if A is false, then you do S2. So what I have achieved here, I have taken the program in this slide, which says if A and B are both true, do S1, else do S2. And I have broken it up like this. I said if A is true and B is true, do S1. Else, which means if A is true and B is false, do S2. If A itself is false, don't bother about checking B because A and B is going to be false. Directly do S2. So this captures exactly the same semantics as this program. But It is rewritten to ensure that each predicate here has exactly one clause. So there are two predicates, one just has clause A, one just has clause B. I have eliminated the predicates containing two clauses here. And this is the new control structure that I have arrived at. Now this doesn't look too bad, but typical experienced programmers will not like this control structure. There are several disadvantages to it. One is people don't like the fact that this entire code segment S2 gets repeated here. That's not considered good programming practice at all, and we can't avoid it here because our goal was to remove the and that was there in the previous predicate. In that process we ended up creating another copy of the code for S2. It is not considered a good programming practice. And the other thing is, now let's consider predicate coverage for this transform program. Remember, the conjecture was this is the transform program. I have removed predicates with multiple clauses. If I achieve predicate coverage in this, it will mean that achieving appropriate active clause coverage in this original program. What we will show is that predicate coverage in this transform program will not satisfy CACC criteria for the original program. What is predicate coverage for this transform program? Predicate coverage for this transform program will need three test cases. First one is A is true, B is true. That will reach this statement S1. Second one is A is true, B is false. That will reach this statement S2. The third one, which is A is false, as I told you, but B could be either false or true, which means A false and B false, or A false and B true. Both these test cases will reach this S2, right? So the first test case for predicate coverage is both A and B are true, reach S1. Second test case is A is true, B is false, so reach this S2. The third test case, which needs to reach this copy of S2, can be achieved in two ways. One is both A and B could be false, or A could be false and B could be true. Both of them will reach the second copy of S2. So that's what is given here. But let's say I have a choice here in the third case, right? For either taking both of them to be false or A to be false and B to be true. But let's say I take both of them to be false. So the final set of test cases that I choose for predicate coverage are true, true to reach S1, true, false from the second item to reach S2, the first occurrence of S2, and from the third one I choose false, false to reach the second occurrence of S2. So this satisfies predicate coverage for the transform program, but it does not satisfy CACC for the original program. CACC for the original program, as we had discussed, had needed three test cases: A true, B true, A true, B false, and A false, B true. This was the only option left. Whereas in predicate coverage, I had the choice between choosing this or this, and I decided to choose both to be false. Because of that, I don't satisfy CACC, but I satisfy predicate coverage. So clearly the conjecture that you transform the program, break up predicates with more than one clauses into predicates with single clause, and try to do predicate coverage on the transform program that will be equivalent to CACC or GACC on the given program. That is not true for this example. Also, the transform program has this not so welcome feature of the code fragment S2 being copied ditto twice. That's usually not accepted. So I'll show you one more example to understand the same issue, but we'll look at it from a slightly different perspective. Here is an example that has a predicate with three clauses that are connected like this: A and B, or with C. If A and B or C is true, then you do S1, else you do S2. Right? So this is easy to read, if you notice, because I just can read this directly. Any programmer will understand what is happening here. It says if A and B is true or C is true, then you do S1. If it's the case that both of them are false, in which case the whole thing is false, then you do S2. Now let's attempt to rewrite this program. You can attempt in several different ways. Whatever ways you attempt, you'll realize that you'll get a very long program with several occurrences of S1 and S2 repeated, and it'll have a very ugly looking control structure. So here is one attempt at rewriting the program. So if you look at this itself, you realize that this looks very complicated, right? And quite difficult to understand. Unlike this is neat. The only thing that you had here was you had a predicate with 3 clauses, but otherwise it's quite neat and simple. For some reason you wanted to eliminate this predicate with 3 clauses, but you wanted to retain a new program where each predicate has a single clause with exactly the same meaning. And here is one attempt to rewrite it. How do I read this? I read this as follows. I say if A is true, then you check if B is true. If B is also true, then you check if C is true. Which means if I'm here, if C becomes true, then what does it mean? It means all 3, A, B and C are true. Then what do? You do S1. If C is not true, but A and B are both true, then you still do S1. That correctly fits with the semantics of this program, right? If A and B are both true and C is either true or false, then this whole thing will be true. All the cases I do S1. So I have simulated it till here. Now let's look at this part. This part has an else that corresponds to this B. So we are in a situation where if A is true but B is false, which is this else, then you can still do S1 if C is true, because that's what the semantics of this predicate is. So you check if C is true, then you do S1. If C is false and B is false, which means this whole predicate is going to be false, then you have to do S2. So then you do S2. Is that clear? So now let's go continue. We have not finished all the cases. So now let's look at this else. This else, if you go straight up, corresponds to this first if, which checks if A is true. So it means if we've reached this else, it means that A is false. So I check if B is still true. A and B will be false. But if C is true, then the OR statement of the predicate in this slide becomes true. So I can still do S1. But if C is false, then I do S2. And again, I check if B is false. If C is true, then I do S1. But if C is also false, then I do S2. After this long drawn effort, I have finally achieved to rewrite the program to capture exactly the same meaning as this predicate. But look at this program. You would agree with me that it looks completely ugly and unreadable. Just because I didn't want this predicate, I tried to attempt a transformation and that resulted in this. By the way, this is not the only transform program. There are several other ways of transforming it. I just wrote this longest transformation in some sense to illustrate how ugly a transform program can get. But the point that I wanted to illustrate is that whatever is the transform program, it's not unique. This is not the only transform program. You could try to do it and you could probably get a simpler one. The transform program is usually much harder to understand than the given one. You would agree with me because just by seeing this example. And going back to our logical coverage criteria conjecture, which said that predicate coverage on this transform program should be the same as CSCC on the given program. That is also false for this program, as it would illustrate. So here in this slide, I have given you details of correlated active clause coverage for the predicate, which was this. I have written it in terms of logical notations and or, but it's the same predicate A and B or C. That was here A and B or C. Here it's written in programming notation. Here it's written in logical notation, but it's the same predicate. This part, the first 5 columns, illustrates the truth table for the predicate. Predicate had 3 clauses A, B and C. Each clause can take true, false values in turn, and this is the entire truth table that assigns true, false values to A, B and C. And this is how the predicate evaluates. It evaluates to true when all of them are true. It evaluates to false when B and C are false, resulting in the whole thing being false. It also evaluates to false when A and C are false or all 3 are false. So that tells you what the predicate evaluates to. Please don't get confused with this capital T and small t. They both mean true. I have written it as capital T just to illustrate what the resulting truth false values of the predicate is. Now if you see, to achieve predicate coverage on the resulting program, I can choose rows 1, 3, 4, 5 and 8. That will completely achieve predicate coverage. Why is that so? Because if you see, row 8 corresponds to predicate being false, 5 3 and 1 correspond to predicate being true. Row 4 also corresponds to predicate being false. So predicate coverage is achieved on the transformed program where each clause takes turns to be true and false, resulting in the predicate to be true and false. But correlated active clause coverage on the original program, if you work out all the details by computing each clause to be the major clause, do PA, PB, PC, write out the truth table and do that exercise, which I have not given here because we've done it for enough examples. If you do that and do the final marking, the TRs for CACC will happen to be rows 2, 3, 4 and 6. So if you compare the last two columns, you'll realize there is immediately a mismatch, right? Because row 1 satisfies predicate coverage, is not needed for correlated active clause coverage. Row 2 satisfies correlated active clause coverage but does not achieve predicate coverage. Similarly, row 6 satisfies correlated clause coverage, does not achieve predicate coverage, and row 5 satisfies predicate coverage. Rows 5 and 8 satisfy predicate coverage but are not needed for CACC. So there is a lot of mismatch between these two columns, which means that the TRs for CACC and for predicate coverage don't match for this exam. So what I wanted to illustrate to you using these two examples is that predicate transformation is not a good solution to avoid using active clause coverage criteria. Active clause coverage criteria is mandatory for testing safety critical software and is to be proven effective for finding lot of errors, especially for predicates that have 3 or 4 clauses. So it is a good idea to be able to go ahead and use it, and transforming a program to remove those extra clauses in the predicate with the aim of avoiding active clause coverage criteria will not work. They are useful, they are mandatory, and it will be good to get used to it. In fact, to help you get some more practice, I encourage you to look at this book website. Most of the material, as we've seen, is derived from this textbook called Introduction to Software Testing. The book has a very good web page. By now you all should know the web page. In that web page, there is a page that contains web apps. So there is a web app for logic coverage criteria. Here is the URL for that app. So here you can input a predicate and get values for the various active clause coverage criteria and the various inactive clause coverage criteria. I don't think they do predicate and clause coverage because they are easier coverage criteria to meet, but they have this app that works well for ACC and for various ICC also, and try and use it for some predicate of your choice with 3 clauses or 4 clauses. Work out a solution manually, then use the app to see if your answer matches with the answer given by the app. The app slows down a bit for predicate with larger clauses because the underlying problems that it tries to do to get these coverage criteria of each clause determining a predicate are non-trivial problems. So try and use it for predicate with 3 or 4 clauses. That way you can work out the solution on your own and try and see if the solution that you have got is the same as the solution that the web app provides. And feel free to ask me if you have any doubts in the forum. Thank you.